Okay, so these are examples for similarity in right triangles using section 7-4. First, write a similarity statement. So you're given a triangle, you're given what we want to start off with a similarity statement. So all the other triangles that we use here have to go in that same corresponding order. So an easy way to do this is using the dots. So what I mean by that is if I look at the original triangles that are over here, put dots in the corners of the smallest angle, 1 for the smallest angle, 2 for a medium-sized angle, and 3 for the base angles, which will always be the right angle. Then for the next one, same thing for that. So in the smallest angle, put 1 dot, 2 dots, and 3 dots. Then we can easily line these up so that we know what order they should go in. WXZ. WXZ is the small triangle here. So we went in the order of 3 dots, X was 1 dot, and Z was 2 dots in the little triangle. So if I go 3, 1, 2 each time, we should have them in the correct order. So if I go to the medium-sized triangle, 3, 2, 1. 3, that's W. 2 is X. Sorry, 3, 1, 2. 1 is Y. 2 is X. So WYX. Again, that way in that same order, 3, 1, 2. So then for the next one, again, same order, 3, 1, 2. So the big triangle, X is the one with 3, Y has 1, and Z has 2. So that's one way that you can easily set up the correct statement. Now, do you need the numbers over top? No. So again, at the end, if you want to, you can erase those values. You don't need them. All right, you just need that similarity statement. I'm going to leave the last one just so I can take a picture of it when I do the notes. On to, we have a triangle given to us. It says, given triangle PQR is similar to triangle QSR, what is QS? So again, this is talking about the length of QS. Now, there's more than one correct way to solve this. Right now, the way this is set up, it's really just trying to get the idea that we have similar triangles, so it wants us to use proportions, and we need to look at the triangles to see how we can set up the triangles so that they are similar to one another, and we can actually solve. So, first step to do here is we're going to take QS and label that as X. Then I'm going to draw triangle PQR. Well, PQR is the really big triangle. So PQR. PQR. Then QSR. In the same order, QSR. And that's the little triangle here, QSR. So again, I drew them so that they look like these, but I also drew them so that they're standing in the same direction. So this one's been rotated and even reflected so that it looks like it's the same triangle in the same direction. That way it's easier to tell which ones are matching up. Now, QS is in both of these. It's in one of these. This is QS right here. That's what we're trying to solve for. That was X. On this one, we also have a couple other pieces. We know that this is 9, and we know that this is 15. For this triangle, we have PQ is 20, and we have QR is 15. Now, we don't know the hypotenuse side of it, so it is true that there's more than one way to do this. Right now, we're trying to use the idea of similarity, so we're going to set up a proportion. So we can pick a side that we have the X on. So here is X. It's going to match up with the 20 that's on that same corresponding side. Then we have to pick two sides that have numbers. So the 9 and the 15 go together. So 9 and 15. Again, there's more than one correct way to set up that proportion. You could have also done X over 9 and 20 over 15. Again, more than one correct way to set up a proportion. There's at least 4 different ways to set up any proportion. But now when we cross multiply, they're always going to be the same two numbers that are being multiplied, unless we decide to reduce. So on this one, Reducing is an option, because if you have two whole numbers in a fraction that have a common factor, you can reduce. We have a 9, we have a 15. These are both divisible by 3. So reduce by 3. We have 9 divided by 3 is 3. 15 divided by 3 is 5. Now that we have those numbers, cross multiply. X times 5, it's 5x. 20 times 3, well, 20 times 3 is going to give us 60. Divide by 5, x equals 12. Now, since I made x QS, that's my answer. The last example that I'm going to do, so this is just 3 quick examples using similarity and right triangles. This last example uses the idea of geometric mean. Yes, you could solve it by doing proportions, similar to what we did on this last one. And you could set up the geometric mean doing those proportions. And if you did it the same way that our textbook does it, you're going to use proportions and solve. But again, with geometric mean, you can do the formulas for geometric mean, and it saves a little bit of time. So in this figure, I'm going to go ahead and label the different parts so you can see what parts go together and stuff. So for example, we have for the hypotenuse, this is the whole hypotenuse. Then we have, I'm going to call this part 1 and part 2. It doesn't really matter which one you call part 1 and part 2. Then we have leg 1 and leg 2. Well, leg 1 will go next to part 1. So leg 1, leg 2. And then y is our altitude. So now, when we set this up, we have our numbers. We know which parts we have. So if we're trying to find y, which is the altitude, let's go ahead and do that one first. So remember, our equation is altitude equals the geometric mean of part 1 times part 2. So we have y equals part 1, 5, part 2, 15. So now, 5 times 15. 5 times 15 is 75. Now, this is not going to come out to a whole number. So, I said round to nearest tenths place because we haven't talked about simplifying radicals yet in this class. Now, you have simplified radicals in algebra. And actually, I did mention it once a little earlier on. We're going to be doing a lot more with simplifying radicals. So, I'm going to show first how to do this as just a decimal. So, if we were to take the square root of this, then square root of 75 will come out to approximately, and I said tenths place, so actually I need to round this off because it's 8.66, so that'd be 8.7. Or if you wanted to leave this as an exact value, that would mean that we would want to simplify this radical. So the way you could do this if you were simplifying a radical, square root of 75, one way to simplify a radical is by finding the greatest perfect square that goes into it. So 25 is a perfect square. It goes into 75, and it's 25 times 3 is what gives you 75. So now you'd have the square root of 25 and the square root of 3. Square root of 25 is 5. So you'd have 5 radical 3. So our answer as a rounded decimal would be 8.7. Our answer as an exact value would be 5 radical 3. So that's our answer for y. Now, it wanted us to find all 3 missing parts. So we found our altitude. Now we got to do our leg. So for our leg, it's our other formula. Our leg formula was the geometric mean of the adjacent part times the whole. So adjacent part times the whole. So for leg 1, that would mean we're plugging in leg 1, part 1, and the whole. When we do leg 2, we'd be doing part 2 and the whole. Again, the adjacent part, the part that's next to it. So if we're using leg 1, part 1 is next to it. That's the adjacent part. If we're doing leg 2, part 2 is next to it. So using that formula, solving for x, which I had labeled as part 1. Sorry, leg 1. Part 1 would be 5, because that's the adjacent part, the one that's next to the x. And the whole, well, we don't know what the whole is, but we can find that, because 5 and 15, those add up to 20. So 5 and 20. So now, 5 times 20. 5 times 20 is 100. The square root of 100, that comes out to a whole number. We don't have to worry about rounding at all here. It's just 10. So that's our answer for x. Now, for leg 2, we have leg 2 was labeled as z. So now we're solving for z. Part 2, which is, again, the part that's adjacent to this leg. That's why we're using it. And then the whole is 20. So now we have some bigger numbers there. We have 15 times 20, which is going to be 300. And 300 is not something that comes out to a whole number. So if you were to use a calculator and round this off, the square root of 300 is going to come out to approximately, oops, I don't know why I did congruent symbol. I meant to do approximate. Two of the squiggly lines. Approximately 17.32, so it's going to round off to 17.3. If we wanted to leave this as an exact value, then we're going to do the square root of 300. We could break it down into 100 times 3, because 100 is a perfect square. So the square root of 100, square root of 3, square root of 100 is 10. So 10 radical 3. So that would be our z value as a exact value. So we have our rounded answer, we have our exact value, and that is how you use those equations to solve for a leg or an altitude. You could also use it to solve for one of the missing pieces. So if you're given an altitude or given a leg and you're given some of the other parts on that triangle, you could use these as well to find the other pieces. All right, that's it for the video for examples. Tomorrow we will do some practice.